So in today's lesson, we're going to be learning about something that is referred to as the common ion effect. So what I want to do is I want to present you with a scenario. Okay, I want you to imagine that you have an equilibrium system where you've taken some calcium carbonate, and which is a solid with fairly low solubility. And over time, a small amount of the calcium carbonate dissociates, and we end up with a small concentration of calcium ion and carbonate ion present in solution. So the equilibrium's established. We've got our beaker, with our aqueous solution. There's a little bit of, just a tiny amount of calcium ion and carbonate ion present in solution. And we've got that little bit of calcium carbonate precipitate at the bottom, maybe, likely. Okay, now then what you end up doing is you dissolve a little bit of calcium chloride into the solution. Now, calcium chloride is a highly soluble salt. But I'm hoping what you notice is that there is an ion that calcium chloride has that's in common with the ions present in this equilibrium system that's in question. So what do you think is going to happen? Well, because the calcium chloride has those calcium ions, that's going to have an impact on this equilibrium system. So by and large, by adding some calcium ion to the solution, I am disrupting this equilibrium. So what's going to be the consequence? What's going to happen at equilibrium if I add extra calcium ions? Well, I'm hoping that you would say that this will cause a shift in the equilibrium towards the left, right? Just like Le Chatelier's principle would indicate, if we add extra calcium into this situation, we're setting this equilibrium off balance. This system's going to want to get rid of the excess calcium, and that will cause a shift to the left. All right, so let's talk about what the consequences of this are. Like, what are the real life, why does this matter? Okay, so let's keep talking about this. So the consequences of the common ion effect at equilibrium are this. We're going to be able to dissolve less calcium carbonate in solution. So in other words, by adding a common ion, we cause the equilibrium to shift so that there's more of this precipitate present. So calcium carbonate, less of it will be able to dissolve as a function of that. And we'll see more precipitate, right? So in fact, if I were to add that calcium carbonate to an equilibrium system, what I would see is I would see a white precipitate forming in solution, and then a whole new equilibrium position would have to be established. Now, what is the real life sort of application of this? Well, I would say that in wastewater management, where we're trying to get rid of certain materials that are present, we want to precipitate materials out. We want to be really careful about how much of a particular substance we're adding so that we precipitate out what we want to precipitate out, but maybe not some of the other pieces. So in wastewater management, causing certain particles to precipitate out is an advantage, but all in good balance. In the next portion, what we're going to do is we're going to look at some calculations involved in with the common ion effect, and you're going to see that it's not so dissimilar to what we've seen with our basic KSP calculations. All right, so we're going to start off with a pretty typical question that you might see, type of calculation you might see involving the common ion effect. So the question reads, what is the molar solubility of PbI2 in a 0.1 mole per liter sodium iodide solution? The KSP for PbI2 is this value. Okay, so just a reminder, a question like this may not always indicate the KSP in the question itself. So remember that at the back of your textbook in the appendix section, you will be able to see a table for giving the KSP values for a whole host of solids with low solubility. Okay, so now let's talk about language here. what is the molar solubility? Really is just saying how soluble is PbI2 in moles per liter. And so that's really all it's asking. But we're saying, well, what is it in a solution of NaI? Now, the KSP here is given for PbI2, which tells us very clearly that the equilibrium system that we're concerned about is this one, the PbI2 dissociating to make Pb2 plus 2I minus. Now, but what about this NaI business here, right? Like what is that and how is that involved? Well, that is our common ion. And so I know, for instance, that this particular substance is going to have the iodine in common with our equilibrium system. So it's going to cause that shift to the left that we just spoke about. Now, students are sometimes confused by this, and so one trick that I would say for you to orient yourself as to which of these compounds is the actual equilibrium is to use a solubility chart. So I'm going to look at, PbI2. Here's I minus, and I minus with Pb2 plus creates a low solubility. It has very low solubility. That's what's telling me that is the thing that's going to have a KSP associated with it. However, NaI is, contains sodium, and all group 1 compounds have high solubility in water. So the thing that is highly soluble is not going to be in a position to be in equilibrium. That's going to dissociate to completion because it's highly soluble. So we're not going to be concerned about its KSP. We're going to be concerned about the KSP of this substance with very low solubility. Okay, so let's carry on with this. What we're going to do is we're going to create an ice chart just as we have in previous questions. And I'm going to start to fill this in. So remember, PbI2 is a solid, so it's not going to have a change in concentration. And so we're just going to start to fill in the information that we know. So for instance, in this case, I have NaI as my common ion. So although I have 0.00 moles per liter of Pb2 plus at the beginning, I don't have 0.0 of the I minus because of my NaI solution. So I know that the concentration of I minus initially in solution is going to be equal to the concentration of NaI, because for every one NaI that dissociates, there's only one I minus ion that is liberated. So that will allow me to say, all right, well, that means that the initial concentration of I minus is 0.10 moles per liter. So that's in fact what I'm going to be putting into my chart. Now, I'm going to go ahead and continue filling in my ice chart just as I normally would. I know that since I have no Pb2 plus at the onset, its concentration is going to only increase. And all reactants and products have to change in the same direction. So I know that my I minus is going to increase by 2x because, of course, I have the coefficient of 2 here. So filling out my ice chart, I have expressions for my equilibrium concentrations, of x and 0.10 plus 2x. And so I would consider this to be the first step that is complete. And now I'm ready to finish up this question. So what I'm going to do is I'm going to give myself a little bit more space and get rid of this guy and continue on. There we go. So I'm going to do this part, I think, in green just to separate it. So I know that the KSP in this case is going to be equal to the concentration of Pb2 plus times the concentration of I minus squared. And again, I would encourage you not to skip this step because, of course, I tend to see mistakes when people skip this step. 7.9 times 10 to the negative 9 is equal to x times 0.10 plus 2x squared. Now, in this case, I know that this increase of 2x is going to be very, very small because my KSP is very, very small, which means that the math will allow me to simplify this, and I'm going to just get rid of that 2x entirely so that I don't have to solve a quadratic equation. So that is something that we talked about when we were doing equilibrium calculations, where we can get rid of some small amounts to simplify the math where it is valid to do so. So that simplifies this to so x times 0.10 squared. And now I'm just going to simply input this information into my calculator to solve. And I am getting as my answer 7.9 times 10 to the negative 7. And so that is in moles per liter. So what does that in fact tell me? That tells me that therefore I can say, therefore the molar solubility of my lead 2 iodide is 7.9 times 10 to the power of negative 7 moles per liter, if I add that Na ion. So that's it. That tells me the number of moles in a liter of the substance that will dissolve given the addition of that sodium iodide in solution. Okay, let's go on to another question. So here we go. So in this question it reads, what is the molar solubility of FeOH3, so iron 3 hydroxide, in a solution of 0.050 moles per liter sodium hydroxide? So what I'd like you to do is I'd like you to try this question, see how you make out, and then we'll come back in a minute and go through the solution. Okay, so I'm going to start by just looking at, first of all, what is the equilibrium system in question here. So I'm noticing that sodium hydroxide is here, and because in this case the sodium is with the hydroxide, that means this is a very highly soluble substance. So that is not my equilibrium system that I'm concerned about. Now it does say that hydroxide with most substances does form a substance, it does create a low solubility solid, and so that is what we're concerned about, and that is the subject of our equilibrium calculation. That's our equilibrium system. So I'm going to just go ahead and write out that equation. So the first thing I want to do is I want to write out my reactant, my low solubility solid, and then I'm going to dissociate it. And this is going to dissociate to form iron 3 plus. And again, that's that 3 there that's showing me over here. That using a reverse crossover rule, if you will. And then I know that 3 hydroxides are going to be liberated. And now I'm going to set up my ice chart, my ice box. And I know that because my iron 3 hydroxide is a solid, it's not going to have a change in concentration. Now what I'm going to do is I'm going to focus in on my NaOH. So over on the side here, I'm going to say, well, I know that my concentration of hydroxide initially is going to be the same as the concentration of the sodium hydroxide that was added. In this case, that is 0.050 moles per liter. So that allows me to know that at the onset, before any iron 3 hydroxide dissolves at all, I am going to have this this concentration of sodium hydroxide present. Now the question doesn't give me any kind of information about iron 3 hydroxide being dissolved, so I'm going to use the assumption that there isn't any. And so now that that's the only thing in this question that's going to be different than prior KSP questions. They're both going to increase in concentration by a certain amount that corresponds to their coefficient. So there are 3 hydroxides liberated, so I need 3 times as much of it in comparison to the iron ion that's liberated. So that gives me some equilibrium expression, x and then 0.050 plus 3x. Okay, and so now I'm pretty much set to go. Now, this is the point where students typically get stumped and they're like, but where am I supposed to go next? I can't remember what I'm supposed to do. Well, it's an equilibrium calculation, so chances are you're going to have to write out the equilibrium law. So let's start by doing that. So I'm going to go with my KSP is equal to the concentration of Fe3 plus times the concentration of hydroxide cubed. And if you've gotten this far, you've probably recognized that the question itself didn't give you the KSP value and that you're going to need to seek that out elsewhere. And so if you go to the back of your textbook, what you'll see is the appendix where you'll see the KSP values. You're going to scroll to where it has iron 3 hydroxide. Here it is, 2.6 times 10 to the negative 39. So let me see that. Let me get that right again. 2.6 times 10 to the negative 39. That's pretty insoluble. So here we go. 2.6 times 10 to the negative 39. Very, very small. This stuff is not soluble at all. And so now I'm going to substitute in the expressions I had for each of these. So x, and then I had 0.050 plus 3x all cubed. Now again, when I look at this K value, I can see that it is extremely small, which means that the reaction in question is not going to proceed very far and is not going to liberate a lot of these iron and hydroxide ions. So that means that any increase that's observed is going to be so minuscule that in fact we can go ahead and just dismiss it from a mathematical standpoint. And so that's what we want to do, because we don't want to have to solve a cubic, right? So here we go. I'm going to keep going. 2.6 times 10 to the negative 39 is equal to x times 0.050 all cubed. And so going ahead and solving this question to 2 significant digits, I'm getting 2.1 times 10 to the negative 35. And that would be in moles per liter. Okay, so now is where I'm going to go back to the last question. And look at this. So to the negative 35 moles per liter, that is an extremely small value. So I can tell from that going over here and getting rid of that 3x, you know, the size of x compared to this is so minuscule that I think that was an appropriate and reasonable mathematical process to do. So let's go back here and recognize what we're trying to find. We're trying to find the molar solubility of FeOH2. Now, since I just solved for x, and x represents the molar concentration at equilibrium of Fe3+, since I know that for every 1 Fe3+ that is liberated, there would have had to come from 1 iron 3 hydroxide. In other words, the mole ratio is a 1-to-1 between these two substances. If I solve for how much Fe3+ is in solution at equilibrium, I've actually found out what the molar solubility of FeOH3 is. So I can go ahead and then conclude that over here by saying that, therefore, the molar solubility of iron 3 hydroxide is 2.1 times 10 to the negative 35 moles per liter. So I hope that you found that this okay. And this tends to, the language of these questions is what tends to confuse students. So please reach out with questions that you have, and I'll be more than happy to help you out.